Hello everyone, thank you for joining us today. We are excited to present our project Student Performance Prediction using Hybrid Ensemble model. These are our team members involved in the project, and this is the GitHub link and the deployment link. Let me give you a quick overview of what we'll cover today. We will start with brief introduction to the problem we tackled, then move on to the objectives, the data set and pre-processing, our methodology, a look at some visual outputs, and finally conclude with key findings and future work. The goal of our project is to predict students' final academic performance using machine learning. But instead of using a traditional single model, we built a hybrid ensemble combining three models: random forest, XGBoost, and neural network. What's unique here is that we don't treat all models equally. We use a dynamic weighting mechanism that adjusts models' importance depending on how influential a student's prior grades, G1 and G2 are. This allows our model to adapt to different types of students more effectively. So what we are trying to achieve: first, we wanted to classify students into three categories: low, medium, and high performers. Then we aim to improve accuracy by using hybrid ensemble rather than relying on a single model. The dynamic weighting strategy based on G1 and G2 was introduced to make the model smarter and more adaptive. Finally, we want to create a user-friendly Streamlit interface that educators could actually use to support real-time decision making. Our dataset came from the UCI machine learning repository, and it included 395 student records with 32 features. These features covered a wide range from demographics like gender and age to behavioral patterns like study time and alcohol use to academic history like grades from earlier terms. The final grade G3 was converted into three categories: low, medium, and high. We also did standard pre-processing steps like label encoding for categorical variables and normalization for numeric ones. The dataset was split into 80:20 ratio with training and testing respectively. We started by cleaning and transforming the UCI dataset. One key decision was removing the school feature so the model learns from the student behavior and demographics, not institutional patterns. We then used standard encoding and normalization techniques before splitting the data for training and testing. Instead of relying on just one algorithm, we combined three complementary models. Random forest offers stability and interpretability, XGBoost brings fine-tuned precision, and neural networks capture nonlinear grade dependencies. What's unique here is the dynamic weighting logic. If prior grades G1 and G2 are highly predictive, we increase the weight of the neural network since it's better at modeling grade trends. Each model brings something unique. For example, random forest is good with noise and diverse data types. XGBoost shines with structured patterns. Neural networks are excellent when prior grades dominate. So combining them makes our model smarter and more adaptable. This is the weighted prediction formula that we have used in our project. These are the weights assigned to each model's prediction, and these are the probabilities that individual models predict for the class. For model building, we first implemented each of three individual models using scikit-learn and keras. The random forest had 100 trees. XGBoost was tuned using early stopping, and the neural networks had two hidden layers. All models were trained on the scaled data. We chose parameters to balance accuracy and training speed, keeping the pipeline clean for deployment later. This is the core of our innovation, the dynamic weighting logic. During training, we measure how important G1 and G2 are using feature importance from the random forest. If they contribute more than 50% together, we assume prior grades are the dominant predictor. In such cases, we shift more weight to the neural network. which is better at modeling grade related patterns. We evaluated models' performance using accuracy, precision, recall, and F1 score, especially for each grade category. Finally, we built a Streamlit interface where educators can input 32 student features and get a predicted along with confident scores and top feature contributors. This makes the model usable behind research in real classrooms for academic planning tools. These are the visuals of our project where we will enter the students' details like their gender, their mother's employment, father's employment, and get the prediction result whether the student is coming under low category, medium, or high. So what did we achieve? We built a predictive system that achieved 85% accuracy while also being interpretable and adaptive. It can help educators make informed decisions early instead of waiting for students to fail. In future, we plan to validate the model on larger and more diverse data sets, fine-tune the dynamic weighting logic, and make the interface even more interactive, possibly integrating feedback or real-time inputs from the teachers or students. Thank you for your time and attention. You can find our code on GitHub and also try out our model on Streamlit deployment link that we have provided in the first slide. Thank you once again.